Hello everyone. Today we are going to start CMOS inverters. So, if you have not seen the previous lectures, please go through the previous lectures and see the fundamentals related to the MOSFET. So now, before starting the CMOS inverters, let me tell you that the things which we will require to discuss the CMOS inverters are the this current voltage equations of MOSFETs. So if you know the current voltage equations of MOSFETs, then things will be very easy for you, because you see, whenever we use the MOSFETs for inverters, then what happens is the MOSFET works in different regions. So depending upon which region the MOSFET is working, you have to use the equations related to that region. So if the MOSFET is working in the linear region, then we have to use the linear region equation. If the MOSFET is working in the saturation region, then we have to use the saturation region equation according to the conditions, the input conditions. So if the device satisfies the input condition for the linear region, then the device will work in the linear region and the output current will be governed by the linear region equation. Whereas if it satisfies the saturation region equation, then saturation region input conditions, then the output current will be given by the saturation region equation. So that's what the important thing is. Okay, so before moving on to, so let's move on to the things. So as far as we know, the inverter, so this inverter which we are going to discuss here is not different from the other inverters which you have studied so far. The only difference is that the inverters which we are going to implement in this course will be implemented with the help of MOSFETs rather. So otherwise, apart from that, earlier you might have studied the inverters with other circuits, with other devices. So that is also useful. And how it is useful is we can understand that the basic symbol for an inverter looks something like the symbol which is shown in the figure A. Okay, so if you give some input A, and the output will be exactly opposite of the input. So if you provide, let's say the output is B and the input is A, so then if your input is 0, then the inverter will give you the output as 1, whereas if the input is 1, then the output will be 0, because inverter means that it is inverting the input. Okay, so you see, if we try to plot this on a curve on which the x-axis is your input voltage, that is A here in this case, and the output characteristics is your plotted on the y-axis, then what will happen is you can see that when your input is low, okay, is on the lower side, then you can easily see that if you can see this input is on the lower side, then the output will be high, because if input is low, then as per the inverter this functionality, when the input is low, then the output should be high. Otherwise, if the input is in this region, high region, because it is high from a certain value, then the output is low. So you see the output is getting low in this case. So this is what the thing is. So you see, so the basic, and this plot which on which you plot the input on the x-axis and the input voltage on the x-axis and the output voltage on the y-axis, this curve is called your voltage transfer characteristics. So it is nothing but the transfer of voltage from the input to the output. So you are plotting the input voltage, the output voltage with respect to the input voltage. So this is called your voltage transfer characteristics, and this is the voltage transfer characteristics for an ideal inverter. Why an ideal inverter? Because the switching is taking place instantaneously at a certain input voltage, at the same input voltage, if you see, the output is 0 as well as 1, which is nearly impossible to attain practically. But to start with, we can see that the basic inverter in the ideal scenario will look something like that, and the VTC of the inverter will look like this. So this is the VTC of an ideal inverter. And why it is important? Because whenever we are going to implement the inverter with any of the components, then at that time our aim will be to get this ideal characteristics. Probably we'll try to do many things to get this, but whatever we do will not be able to get this characteristics. But our target is to get this characteristics. So that is why these characteristics we should keep into the back of the mind, so that we can refer to the to this characteristics whenever we get a practical characteristics, so that to match it with the practical characteristics with the ideal characteristics, so that how much satisfactory our this inverter we have realized. So to just compare that, we need to keep this into back of our mind. Okay. So you see, now if you try to understand this CMOS inverter with the basic, the first order explanation, so then you see what happens. If you see, then your CMOS inverter is nothing but let's say CMOS. So why we call it CMOS? Okay. So basically we have seen in the last slide that what is an inverter. Now if I call it a basic CMOS inverter, then why we call it as a CMOS inverter? We call it as a CMOS inverter because the two devices which we use here, okay, to realize the two components, which is called as the pull-up network and the pull-down network, we use two switches. So these two switches are basically used to realize either as a switch or as a resistance. So let's first see that if suppose I want to realize the inverter with the help of, let's say, switches. Okay, we will go to the CMOS inverter later on, but let's say if we try to realize the circuit with the help of two switches, then what will happen? So you see, if your input Vin is 5 volts and you have connected, let's say, two switches. So in one of the case, when the top switch is open, so what will happen? The output will be connected with the ground through the lower switch. And in this case, let's say the lower switch is giving you some finite resistance, okay, whereas the upper switch is, let's say, is an ideal switch and it is providing you very high resistance, or sort of open circuit. Okay. In the other case, so this is one situation, and in the other situation, what will happen? If in the first case, what will happen? The output will be connected to the ground via some resistance, whereas the output is completely disconnected from the supply voltage, from the VDD. Okay. Whereas in the other case, what happens? Our output gets connected with, output gets connected with VDD via some resistance, which is RP, whereas on the lower side, if we see, that switch is open completely. So you see, the output will not be connected with the ground, but it will be connected with your resistance directly. So this is what the basic first order, the very basic level, if we see the two switches, then it will look something like this. Then you see what will happen. So in this case, what will happen? If you, the same circuits in the first case and the second case. So you see, when your input is low initially, and let's say you have made these connections from the RP, okay, via RP to the VDD. Then what will happen? The output will get charged to some potential which is equal to VDD ideally. So your output will reach up to VDD. Okay. Then in the other case, it will happen. What will happen if you if that upper switch is disconnected? Then your capacitor is initially, let's say, it is charged. So then it will get discharged via RN. So you see what will happen? The output terminal will get connected to the ground via your RN. So the output will get whatever voltage you have initially on the capacitance will get discharged through the resistance. So the point here is, like, whenever there is charging of the capacitor at the output node or the discharging of the capacitor at the output node, which is CL here, then what happens? The charging or the discharging time is governed by your whatever components coming into the path. So here in the first case, the components which are coming in the path are RP and CL. So the charging time, because the capacitor is charging in this case. So the point here is the charging time will be dependent upon RP, the values of RP and CL, because it is an RC circuit. So it is an RC time constant. So the time which the circuit will take, the output will take to reach the maximum value will depend upon your RC time constant. Whereas in the other case, the discharging time constant will depend upon not only upon the CL but also on the RN. Okay. So the point is, as you have understood it, that the charging or the discharging time depends upon your resistance values of the two switches. And as we will see later on, that the values of RP and RN may be equal or may not be equal. So if they are equal, then the time constants will be equal, because CL is common in the charging as well as in the discharging path. So if if the values of both the RP and RN are equal, then the charging and the discharging times will be equal. But if the values of RP and RN are different, then the charging and the discharging time may be different. Okay, so that's what the point is. So you should understand it, the transient response as well. So okay, this was like about the basic. If you try to realize the inverter with the help of two switches, then how it looks like. But usually we don't realize it with the help of switches, but we realize it with the help of some other components. So the two components which we use here are like, one is called the load component, which you can see, which is connected to the VDD, whereas the other component is called the driver. Okay, so the driver, why it is called the driver? Because this is the component which is actually controlling your output voltage, okay, which is responsible to control the output voltage. Although the load, okay, the load which you can use here, this is the circuit which you can see here is a general circuit. Okay, so basically whenever you try to realize an inverter, and why we want to realize an inverter, because this inverter, if once you are able to realize this inverter with the help of two MOSFETs, okay, then this is the very basic circuit which can be used to implement this higher level circuits. If suppose you want to implement a NAND gate or a NOR gate or any complex circuit, so then that circuit will be composed of many inverters. So if once we are able to analyze that inverter properly, then what will happen? We can on the same lines we can analyze any circuit. So that is why that this inverter analysis is very important for us. So you see, so today, in this today's class, we are going to completely discuss this CMOS inverters. Okay, complete analysis of CMOS inverters. So that if you want to calculate the various related voltages for this, we can easily calculate for it for any CMOS inverter. So you see, that's what the thing is. So if you want to calculate the this various voltages related to the inverter, so first of all we have to realize the inverter itself. So your inverter is basically consists of a load component and a driver component. So a driver component basically we use as an NMOS, whereas for load we can use either as a resistance or as a we can use either a resistance there or we can use a MOSFET. Okay, a MOSFET can be here, which we may use here, can be a depletion type or can be enhancement type. It can be NMOS or a PMOS. Okay, so if we use a resistance, then the circuit will be something different. The voltage transfer characteristics, as in the previous case, in the ideal case, you have seen that how it will look like. But in the practical cases, the VTC will look like something which you can see here in the right diagram. Okay, so it will look something like that for practical circuits. Now, the shape of the VTC will depend upon the type of load which you use. Okay, if you use a resistive load, then the shape of the VTC will be little different. If you use a NMOS enhancement type of load, then the shape of the VTC will be different from what you got it for, for the resistive case. Okay, for the resistive load case. If you use a depletion type of NMOS, then the characteristics will be further different, can be further different. Okay, so you see, depending upon the type of load which you use, the shape of the VTC and the levels of the values of the this various voltages, the important voltages which we will derive later on, will change. The values of this various voltages will change depending upon the type of load which you use here. Okay, so that is why this load is important. So depending upon the load, which type of load you are using. If you are using a resistance, then you call it a resistive load inverter. Okay, if you use NMOS enhancement type of NMOS in the load, then you call it enhancement type NMOS this inverter. Okay, if you use a P-type enhancement mode device, then you call it something else, which we basically call it as a CMOS inverter, because the two components which are exactly complementary to each other, because the driver is your enhancement type NMOS device and the load is enhancement type P-type device. So the two devices are now exactly opposite of each other. So if you use the load as a PMOS enhancement device and the driver as a NMOS enhancement device, then you call it as a CMOS inverter. Then in that case, the VTC will be something different. But whatever VTC, whatever type of VTC you have, the shape of the VTC may change, but the voltages which you have defined here, let me enlarge the figure and you will see that the various voltages which you can see here will come in any type of inverter. Okay, so the nomenclature or the definition of this voltages is more important for any type of inverter, and the formulas or how to calculate this particular voltages is also very important. So in today's class we are going to basically calculate this various voltages, okay, which you can see here in this VTC plot, that this voltages are VOH on the output axis. You can see VOH and VOL, whereas on the input axis you can see some other voltages which are like VIL, okay, input side low voltage, VTH, threshold voltage of the this inverter itself. Okay, this is different from the threshold voltage of your NMOS or the PMOS. So basically in your this CMOS circuits, you have three threshold voltages: threshold voltage of NMOS, which you denote by VTN; threshold voltage of PMOS, which you denote by VTP. Okay, VTN is always positive, VTP is always negative. Okay, whereas VTH is the threshold voltage of the inverter, which is different from the threshold voltage of NMOS or the PMOS. Okay, now so this is also important for us, and the other voltage is VOH. So usually VOH on the input side is equal to the VOH on the output side. Okay, so these are the various important voltages, and apart from this there are two other points which you can, VIL and VOL, as you can see, VIL and VIH. And how you differentiate, how you define this VIL and VIH, it depends upon the slope of this curve. So at the points where the slope of the curve is equal to -1, so those points are defined as VIL on the lower side, and on the higher side of the input side it is defined as VIH. And why these points are important, why this slope we have taken as -1, that we will see later on. Okay, but this slope, this points for any type of inverter is defined like this only. Okay. Now here we could have discussed the various inverters with different type of loads, but those different type of loads are not that much useful. They have certain disadvantages, and those circuits are not basically used in your VLSI. So we are not going to discuss them in detail. But if you want to understand the things in detail, obviously you can revise your earlier courses, or you can go through the book and you can understand the things. Here in today's class, I'll discuss only the CMOS inverter. Okay, that is, I'll use the load as a PMOS enhancement device, not any other device. Obviously we can use them, and we can use any of the device, and we can analyze the circuit. The analysis of the circuit will be exactly same. Okay, you have to just identify the various regions only. We will identify everything for CMOS inverters, okay, not for the other type of inverters. But if you want, you can do it as the process will be same. And for every inverter, we have to determine the formulas for this various voltages. Obviously, if we will analyze the CMOS inverter, we will only define, or we will only determine or derive the equations for this related voltage for CMOS inverter and not for the any other inverter. Okay. So you see, now if we consider these voltages, then for your CMOS inverter or for any type of inverter, this noise margin becomes a very important parameter. So you see, what is noise margin? So noise margin is nothing but it is, if you try to define the noise margin, the physical significance of noise margin, and what is basically the noise margin is. So noise margin is nothing but it is a sort of tolerance which the circuit have. Okay, which the circuit, there is a certain range on the input side which the circuit can tolerate without changing the output. Okay, so you see, in the analog circuit, what happens if we change the input voltage by a small value, then the same change can be reflected on the output side. But in the digital circuits, basically, we go for the digital circuits basically for this reason only, because the digital circuits provides you better noise margin or the higher noise margin compared to your analog circuits. So because of that, what happens is, if there is any small variations in the input side, then also your output doesn't change and it remains the same as desired. So you see, that is a very important thing. Earlier it was very difficult to to make a circuit, because whenever there is a slight noise or slight variation into the input parameters, then what happens, because of the noise or any other thing, then the output also changes simultaneously accordingly to the input, according to the input and output relationship. Okay, but for the digital circuits, this noise margin plays very important role. So you see how to calculate this noise margins. So this noise margin, and you see this noise margin is not a single value. Okay, as you can see, as we have defined the inverter, so there are two levels in the inverter, lower side and the higher side. So the lower side will have a separate noise margin, whereas the higher side will have a different noise margin. So we have to calculate the noise margin separately for the higher side as well as for the lower side. So if we want to calculate the noise margin on the lower side, then we can define it as NML. Okay, the noise margin is usually denoted by NM, and L is for the lower side. So NML. Okay, so NML is defined as VIL minus VOL. Okay, why VIL minus VOL? That we will see later on. But this is how we define the noise margin. Okay, and on the higher side, the noise margin can be defined as NMH. Okay, it can be denoted as NMH, and you can calculate it by this formula, VOH minus VIH. Now, to calculate the noise margin for any circuit, what we have to do is we have to calculate these various levels, or this 4 important voltage values. If you are able to calculate this 4 voltage values, then obviously by substituting directly them in this equation, we can calculate the noise margin. Right. Okay, so how we define this various VOL and VOH? So in the previous this circuit, if you see, so you see what is your VOL and VOH. VOH is the maximum voltage of the output side. So you see it is the maximum voltage on the output side. So you see VOH. So it is in this slide particularly, you can see maximum output voltage when the output level is logic 1. So this is how you define your VOH. Then what is your VOL? VOL is, you can see on the y-axis, it is on the lower side near the 0. So it is how you define it. It is the minimum output voltage. It is the minimum output voltage when your output level is logic 0. If your output level is, the minimum voltage which you want to interpret at it as logic 0, so that voltage will be denoted as VOL. Okay. Now, how you define your VIL and VIH? VIL is, as you can see, it is on the input axis. So obviously all the voltages will be for the input side. So you see, if your input voltage remains below VIL, then the output is high. So then you see what happens. How you define VIL? It is that maximum value of the input voltage. You see here, it is that maximum input value of the input voltage which can be interpreted as logic 0. Because if your input lies in this range, then your output will be high. So that is why this is the maximum input voltage which can be interpreted as logic 0. Okay. Whereas how you define VIH? It is on the higher side. It is on the input axis, but this is the higher value. So how you define VIH? The definition of the VIH is, it is the minimum input voltage which can be interpreted as logic 1. Because you see, if your input voltage is above VIH, then your output goes to 0. So this is the minimum, this is your minimum input voltage which can be interpreted as logic 1. So this is how you define your noise margin. Okay, and this noise margin plays very important role if you cascade certain inverters. Why it plays very important role? When you this cascade various inverters, back to back, when you connect some inverters back to back, okay, one after the other, then this your noise margin plays important role. Why it plays important role is, the reason is, if let's say you apply some let's say VOH or the input to the first inverter, there are 3 inverters which are connected here, and between the 2 inverters there is some wire, okay, some interconnect wire. So that interconnect is susceptible to the noise, to the nearby noise. So then what happens? Let's try to understand this thing. So then you see, you'll automatically understand the importance of noise margin if you understand this diagram. So what happens if, let's suppose, at the input of this circuit, if let's say here I apply this some input, and that is, let's say, 1. So if I apply 1 as the input, then here at the output what happen? The output will be 0, because if input is 1, if input here is 1, then your output here is 0, right? Now if this output is, if the output of the first inverter is 0, then what will happen? Now this output will reach to the should become the input of the second inverter. But in between this output of the first inverter and the input of the second inverter, there is some wire, okay, and that wire is susceptible to the nearby noises. So let's say because of this noise, this VOL, whatever you get at the output of the first inverter, doesn't remain the same, okay, at the input of the second inverter, but it changes. It changes. So if suppose this VOL changes and it is like less than, there is, if VOL reduces and it becomes less than VIL, then there is no problem, okay, then there is no problem, because VIL is, and this is the maximum voltage which you can apply here. If you apply little lesser voltage, then also there is not a problem, and the input voltage to the second inverter will be considered as VIL. If this is, VIL is the maximum input voltage which can be interpreted as logic 0. So your input to the second inverter becomes 0, okay, and the output in this case of the second inverter will be your 1, right? So no problem up till now. But if the input, rather than decreasing, it becomes increased, okay, it increases, okay, rather than decreasing, it becomes, let's say, it increases, then what happens? Your value which is reaching at the input of the second inverter, let's say, is above VIL, okay, gets above VIL, then what happens? This will, the input to the second inverter will not be treated as 0, and so the output will not be VOH, okay, will not be treated as 1. So you see there is a problem because of noise. If the noise decreases VOL below VIL, then there is not a problem and the circuit will work properly. But if the noise increases VIL above this, increases this VOL above VIL, then there is a problem, okay, then the circuit will not work properly, okay, or the input will not be interpreted properly. So this is what happens. And similarly, the same situation happen with the output of the second inverter and the input of the third inverter, okay. So you see, so this range, okay, which you can see in the next slide, so this range, okay, which is this range. So if I'm talking about this range, which is your VIL minus VOL, so this is the tolerance, okay, this is the tolerance which is allowed on the input side, okay, input side of any inverter. So if this much voltage variation is there because of any reason, then your output doesn't change, okay, and this is why this is called the noise margin. So this noise margin on the lower side is denoted by VIL minus VOL. On the upper side, it is denoted by this. So this region, NMH. This is your upper side noise margin. So you see, your input voltage should be, if it is below VIL, then it will be treated as 0 voltage. If it is above VIH, then it will be treated as 1. But if suppose it is in the between, it is between VIL and VIH, okay, in the transition region, then it can't be considered as 0 or 1, and that is what the reason is, because of which this is what the reason is, because of which you want this the slope of this curves, VIL and VIH, as -1. You define those points as -1, because in this region, in the transition region, the gain of the inverter is very high, okay. If the gain becomes very high, then the circuit will not be in the stable region, okay. It will try to, it is dynamic in this region. So, and if you're in this region, if particularly any noise comes, then it will be magnified, the amplification will be too much, the noise will be amplified, okay, at the output end. But if you consider the boundaries, let me move to the previous slide. So if you consider this particular V in and V out as your boundaries, VIL and VIH as the boundaries to the input voltage, then you limit your gain, okay. You limit your gain such that if your noise comes in this range, it will not be amplified. Whereas if the circuit works between VIL and VIH, and in that case if the noise comes, then it will be amplified, and if the noise amplifies, then your circuit won't work properly, the output will not be interpreted properly. So that is why these points are important, okay. VIL and VIH points, these points are defined as dV out upon dV in are the points at which the slope is equal to -1, okay. So this is what the importance of this point, okay. Now the other parameter which we will like to calculate for any circuit is your power consumption, DC power dissipation, okay. So the important thing is, for your CMOS circuits, the DC power dissipation is almost 0. Why? We will see it later on. But if you want to calculate the DC power dissipation for any circuit, then we can calculate it as the average power, because let's say the circuit is on for one half cycle. Let's say it is working in one half region, in the upper half region as a on circuit in one half region, and in the other half region it is working as a off switch. so you can average that current. So that's what the reason is. So power dissipation we will calculate later on. For CMOS circuits, the static power dissipation or the DC power dissipation is almost zero, so we won't calculate this. But for the dynamic power dissipation will not be calculated with this equation, it will be calculated with certain other equation. So we'll see later on, we'll see that equation later on. But this equation may be helpful if you are analyzing other inverters. So that's why I have shown you this equation. Okay. Now let's come to the CMOS inverter, which is our today's this main topic. So you see our CMOS inverter, and before moving on to the CMOS inverter, we will define some important voltages. Okay, so whatever up till now whatever we have covered, so these are the parameters which will require to calculate for any CMOS inverter. So we have defined the various parameters and the various voltages which will require to calculate for a CMOS inverter, and how we will calculate and what is the importance of those particular voltages. So that's why what we have defined so far, and they are not only important for CMOS inverters but for any type of inverter. So basically we have given the various important terminologies required for the inverter. Now let's move on to the inverter, and we'll try to calculate the various voltages for the CMOS inverter itself. Okay, so you see our CMOS inverter is basically looks like this. So let me magnify the circuit first of all. So if I magnify the circuit, then the circuit will look something like this. So you see this is our on the left side, the circuit which you can see is your CMOS inverter. So your CMOS inverter have PMOS and NMOS. So PMOS let's say is working as a load, whereas the NMOS will work as a driver. Okay. So okay, this is the circuit. So both the gates are connected together, and the body terminal is connected to the maximum negative voltage in case of NMOS and maximum positive voltage in case of PMOS. And the reason to connect the body terminal to the extreme voltages is to reverse bias the source and the drain junctions. Underneath, I mean the junctions which are coming underneath the source and the drain junctions, you need to reverse bias them. So just to reverse bias them properly and satisfactorily, so that they never becomes forward bias, we connect the body terminal to the extreme positive voltage in case of PMOS and extreme negative in case of NMOS. So to make an inverter, what we do, the bodies are connected as I have already explained you, whereas the sources of the device, the source of the NMOS is connected to the ground, whereas the source of the PMOS is connected to the VDD. Okay, and the drains are connected together, and from this connection we take the output. So the input we apply on the connections of the gate terminal, and the output we take from the connections of the this drain terminal. Right. Now to understand the functionality of the CMOS inverter, let's try to understand it without any equation first, and then we will define certain voltages. Okay, so you see this voltages, will come to these voltages later on. Okay, I'll come to this circuit, the leftmost circuit later on again, but let me try to explain the things as we have discussed in the previous ideal inverter, in case of ideal inverter. So let's say we have two switches. So because these MOSFETs are going to work as switches. Okay, so these are the switches. So usually you have, I mean if you apply some voltage, then one of the switch will become on and the other switch will become off. So you see, as you know from your previous discussions, that your NMOS have a positive threshold voltage and PMOS have a negative threshold voltage. So if you apply Vin, let's say at the Vin you apply some positive voltage, then the NMOS switch will be on, whereas the PMOS switch will be off. Okay, so this switch if on, then the circuit will get completed. The Vout terminal will get connected to the ground terminal via the NMOS switch. So that is important. So this path will be required to disconnect to discharge the your CMOS this output voltage, okay, or the output capacitance. So it is same as what we have seen earlier. Whereas if you want to charge the circuit, then the opposite will be true. Okay, and the other circuit, the rightmost circuit, is the circuit which you will see usually in your books. Okay, so that's what I have shown you here. So NMOS, there are two symbols for NMOS and PMOS. So if you use a body terminal, then in that case you have to show an arrow on the body terminal. If the arrow points inside, then it is a NMOS. If it points outward, then it is a PMOS. But if you don't want to use this symbol, you can use other symbol which is shown in the rightmost diagram, and that is the PMOS is shown with a bubble. Okay, so the symbol of NMOS and PMOS are exactly equal, but I mean exactly same, but the PMOS have a bubble on the gate side, on the gate terminal. So this is what the symbol for NMOS. Now let's move on to the this leftmost circuit again, and let's try to understand this various input voltages, because this input voltages will play very important role in case of your the explanations which we are going to see. Okay, so to understand those explanations, we need to understand these voltages. We'll try to understand these voltages for NMOS, and then for the PMOS also, but you see from the equations we'll easily understand them. So you see, your source terminal of the NMOS is grounded, whereas the gate is connected to some voltage which is Vin. So if I ask you what is VGSN, so VGSN is basically nothing but the potential of gate voltage with respect to the source voltage of an NMOS. N denotes the NMOS. So VGSN is nothing but the potential of the gate terminal with respect to source. Now, as your source is grounded and gate is connected to, let's say, some voltage Vn, so what will be your VGSN? It is nothing but equal to Vn, right? Because your source is grounded and gate is at Vn. So if you find VGSN, it is nothing but Vg minus Vs. As Vg is equal to Vn and Vs is equal to 0, so your VGSN will be equal to Vn. So you see, this is what I have shown in this equation here. So VGSN is equal to Vn, right? Okay. Now what about VDSN? Now VDSN is equal to what? Drain to source voltage. Now source is grounded again, and drain is, let's say, you define this drain as, let's say, V out. Okay, whatever is the potential at this terminal, you call it, let's say, V out. So VDSN is equal to Vd minus Vs for the NMOS device. So Vd is equal to V out and S is equal to 0. So your VDSN will be equal to V out minus 0. So it will be equal to V out, right? So this equation show this. So we have defined VGSN and VDSN. So VGSN will be equal to Vn. Later on, we will not write VGSN. Why I am explaining this? Because in the earlier equations of the drain current, which we have derived for the NMOS and the PMOS, we have seen the equations in terms of VGSN and VDSN. Okay, VGS and VDS and VTH, not in terms of Vin and V out. But when we make an inverter, usually the voltages which we have are Vin and V out. So what we are trying to do is we are trying to represent those equations in terms of Vin and V out rather than VGSN and VDSN. So what I am trying to do is I am trying to represent those VGSN and VDSN in terms of Vin and V out, because these are the voltages which will be used in an inverter. So that's what the reason is, because of which I am showing you these equations. Okay. Now similarly for the PMOS, if you write the equation, then you can see that the source of the PMOS is connected to VDD, right? Whereas the gate is connected to Vin. Now, if I ask you what is your VGSP, okay, so VGSP will be Vg minus Vs for a PMOS. So Vg, excuse me for time. So you see, this is what it is. So as I was discussing, VGSP. So VGSP is your this one. So VGSP is, see how you will write VGSP. VGSP is equal to gate to source. So gate minus source. So VG minus VSP. So VG is your V in, okay, and VS is your VDD. So how you will write VGSP? It is V in minus VDD. So V in minus VDD. Now you can write it as like this: V in minus VDD. Now as this voltages, all voltages to the PMOS we usually denote by negative sign. So rather than writing it as V in minus VDD, we can take minus common and can also write it as minus of, within brackets, VDD minus Vin. Okay. Now what about VDSP? If you write VDSP, it is drain to source of PMOS. So drain is your V out and source is your VDD. So VDSP will be V out minus VDD, right? So if you write it as VDD, V out minus VDD, and you want to take minus common, then what will happen? You can write the equation as V out minus VDD, or if you take minus common, then it will become minus of VDD minus V out. So you see, this voltages are important to understand before moving further. Why this is important, you will see later on, because in every equation which you have derived so far, that is the equation of your ID of NMOS or PMOS, wherever there is VGSP, you have to, in the equation of NMOS, if it is VGSN, you replace that VGSN with Vin, okay, VDSN with V out, and in the equation of this PMOS, you have to replace VGSP with VDD with minus of VDD minus Vin, and VDSP with minus of VDD minus V out. Okay, so this is important. So just keep this into mind and rewrite the equations of your this NMOS and PMOS. So we'll see that in tomorrow's class, and you see, so this is what we have seen so far. So you see, basically these are the equations, and if you'll substitute these equations in the equations of your drain current of NMOS and PMOS, you'll get the equations in terms of equation of NMOS and PMOS in terms of V in and V out. So you try to rewrite them by your own, and then we'll see that in tomorrow's class. So I stop my today's class here itself, and we'll discuss the things in the next class. Okay. So thank you everyone for listening.